Hello students, let us start with definition. Let V and W be vector spaces. Let us form the Cartesian product V cross W is equals to set of all order pair V comma W such that V belongs to capital V and W belongs to capital W. Okay. Define addition and scalar multiplication. Define addition and scalar multiplication on V cross W as V1 order pair V1 comma W1 plus order pair V2 comma W2, which is equals to V1 plus V1 comma W1 plus W2, where V1 order pair V1 comma W1 belongs to order pair V2 comma W2 belongs to V cross W, and alpha into order pair V comma W is equals to order pair alpha V comma alpha W. Alpha is belongs to R and order pair V comma W belongs to capital V cross W. Then V cross W is a vector space. This vector space usually denoted by V in sum n and called the direct product. Not direct product, it is a sum. Direct sum of V and W. Okay. See here, V and W be two vector spaces. Let us define the Cartesian product V cross W is equals to set of all order pair V comma W such that small v belongs to capital V and small w belongs to capital W. Define addition and scalar multiplication. This is the addition and this is the scalar multiplication. This is a vector space and this vector space is called direct sum of V and W. Okay. Note, we can extend direct sum in above definition to define direct sum V1, direct sum V2, direct sum and so on, direct sum Vn of n vectors Vi, 1 is less than or equal to I is less than or equal to n. then it is clear that Rn is equals to R ring sum R ring sum and so on direct sum R. This is up to n times. Okay. This direct sum for only 2 vectors and this direct sum for n vectors. Okay. Let us take one example. Let V is equals to R plus be the set of all positive integers, set of all positive integers, sorry, not integers, this is R plus, so it is real. Define addition of two, define addition of two members x bar comma y bar to be the usual multiplication of members, that is x bar plus y bar. Addition of two members x bar plus y bar is equals to usual multiplication of members, means x bar into y bar. Define scalar multiplication by a scalar k to any x bar belongs to R plus to be x raised to k, that is k into x is equals to x raised to, then show that V is a vector space. Okay, students, see here, this is homework to verify closure axiom, addition axioms and scalar multiplication axioms. Here I will only prove third addition axiom. To give one note, addition axiom. This is third. What is third addition axiom? Existence of zero vector. Okay. Third axiom is existence. Here, see students, addition of two members is nothing but multiplication of two members. Okay. 1 bar is belongs to R plus. Okay. We have to find out zero vector for this set V, such that for any x bar belongs to R plus, what we will get? X bar plus 1 bar is equals to, what is the x bar plus 1 bar is? X bar into 1, which is, sorry, 1 is real number. Okay, here is 1 bar. Okay, sorry, here we have to find zero vector, that's why here is a bar. Don't consider this one as a real number. Okay, so see here, x bar plus 1 bar is x bar into 1 bar. This is nothing but x bar. 0 vector means what? If 0 vector is added to any vector, we will get that vector itself. Then this 0 is called 0 vector. You see here, if we added 1 bar in x bar, we will get x bar. Means this 1 bar is a 0 vector for r plus. Similarly, 1 bar plus x bar is equals to 1 bar into x bar is equals to x bar. So this 1 bar is 0 element or 0 vector. Element and vectors are same. Element in R plus. Okay. So students, write down one note. From this example, we see that 0 element of a vector space may, for vector space I will write v dot s. Vector space may not be usual 0. Means 0 element means not, it is a 0. Okay. So keep in mind that it is 0 element with respect to the operation defined in the set. Okay. See here 0 vector means not a 0 element. Okay. So keep in mind that it is a 0 element with respect to the operation defined in the set. Okay. I hope all of you understand this concept. Okay. Now, our next topic is consequences of axioms. What is next topic? Consequences of axioms. Okay. First theorem is let V be a vector space. Then first is there is only one 0. There is only one 0 in V. And second is each vector has, in V has just one negative in V. This is negative. Okay. Negative in V. Okay. What is first statement? First is there is only one 0 in V. Okay. There is only one 0 in V. Proof. We have to show that there is only one 0 in V. We assume that, suppose that there are two zeros in V. Suppose that 0 bar and 0 dash bar are both 0 objects in V. Are both 0 objects in V. Okay. Therefore, we have 0 bar. 0 bar can be written as 0 bar plus 0 dash bar. Okay. Since 0 dash bar is a 0 in V. Means what? If we add 0 dash bar in 0, we will get 0. Okay. And also, so 0 dash bar is equals to 0 bar plus 0 dash bar. Since 0 bar is a 0 in V, means what? If we add 0 bar in 0 dash bar, we get 0 dash bar. Okay. Students, see here, RHS of these two equations is same. That means this implies 0 bar is nothing but 0 dash bar. Means what? There is only one 0 in V. Therefore, or there is unique 0 in V. There is unique 0 in V. Okay. So here, or write down one note. There is unique 0 vector in any vector space. In any vector space. Always remember that there is always unique 0 vector in any vector space. Okay. Now we will prove second part. What is second part? Second part is each vector in V has a just one negative in V. Okay. Let U bar be a vector. Vectors, say vector, objects, elements, all are same in V. Okay. Suppose that Y bar and Z bar are both negatives of X bar in V. Suppose we have two negatives Y bar and Z bar of X bar in V. Our aim is to show that Y bar is equals to Z bar. Okay. So what happened? Y bar can be written as 0 bar plus Y bar. Okay. First of all, we here write down. We will show that X bar is equals to Y bar. Okay. Y bar is written as 0 bar plus Y bar, obviously, because 0 bar is 0 in V. Okay. 0 in V, which is equals to 0 bar can be written as Z bar plus X bar plus Y bar. 0 bar can be written as Z bar plus X bar. Why this is? Because Z bar is negative of X bar. Means what? Z bar plus X bar is equals to 0 bar. Here Z bar is a negative of X bar. That's why we will get Z bar plus X bar is equals to 0 bar. Okay. Which is equals to Z bar plus X bar plus Y bar. Okay. By here V is a vector space. So here associativity is V. Or we can say that by axiom A2. Okay. Which is equals to Z bar plus 0 bar. Why this is? Because Y bar is a negative of X bar. Since Y bar is negative of X bar, that is X bar plus Y bar is equals to 0 bar. Okay. So, and we know that 0 bar is a 0 in V. That's why we will get Z bar plus 0 bar is equals to Z bar. Therefore, we get Y bar is equals to Z bar. Okay. So, here write down note. I will write down here note. First, the negative of a vector, the negative of a vector u bar in V, and we shall denote the negative of u by minus u bar. Okay, and second one is with above convention, we may define subtraction in V as for u bar and V bar in V, u bar minus V bar is equals to u bar plus minus V bar. Okay, let us take next theorem. So, before this, keep in mind that there is only one, means unique zero vector in V, and for each vector in V there is a unique negative in V. Okay, these are very important results. Now let us see next theorem. Next theorem is, let V be a vector space. Let V be a vector space. U bar a vector or object or element in V, and K be any scalar, then first is 0 into u bar is equals to 0 bar, second is k into 0 bar is equals to 0 bar, third is minus 1 into u bar is equals to minus u bar, and fourth one is k into u bar is equals to 0 bar if and only is either k is equals to 0 or u bar is equals to 0 bar. Okay, first is 0 into 0 bar. Here 0 is scalar and this 0 bar is a vector, so keep 0 into u bar is equals to 0 bar, second is k into 0 bar is equals to 0 bar, third is minus 1 into u bar is equals to minus u bar, fourth one is k into u bar is equals to 0 bar if and only if either k is equals to 0 or u bar is equals to 0. Okay, so we'll see proof of this theorem. First we have to show that this we have, okay, 0 plus 0 can be written as 0. Okay, multiply by u bar on both sides, we will get 0 plus 0 into u bar is equals to 0 dot u bar. Okay, therefore this is 0 dot u bar plus 0 dot u bar, okay, which is equals to 0 dot u bar. In next step, 0 dot u bar plus 0 dot u bar plus minus 0 dot u bar is equals to 0 dot u bar plus minus 0 dot u bar. Adding negative of 0 dot u bar on both sides. So we will get, therefore 0 dot u bar plus, use associative property, associativity of sum, 0 dot u bar plus minus 0 dot u bar is equals to 0 dot u bar plus minus 0 dot u bar. Okay, by axiom A2. Okay, this is nothing but 0 dot u bar plus this is 0 bar. Why this is? Because of axiom A4. Because 0 minus 0 dot u bar is a negative of 0 dot u bar. Okay, which is equals to 0 dot u bar. Sorry, this is again 0 bar, and this 0 bar is a 0 in V. Therefore, 0 dot u bar is equals to 0 bar. Okay, hence we have proved which we want to prove. This is by axiom A3. Okay. Here by axiom A4. Okay. I hope all of you understand. This is the proof of first. Now we will prove second part. In second part, we have to prove k into 0 bar is equals to 0 bar. Okay. For 0 bar belongs to V, we have k into 0 bar can be written as 0 bar plus 0 bar is equals to k into 0 bar. First of all, 0 bar can be written as 0 bar plus 0 bar. Multiply on both sides by k. Okay. So we will get k in, because this is by axiom A3. Why A3? Because 0 bar is a 0 vector in V. Okay. So k into, okay, we will write in detail. 0 bar can be written as 0 bar. Multiply, this is by axiom A3. Because 0 bar is a 0 vector in V. K into 0 bar plus 0 bar is equals to k into 0 bar. Okay. So, here we will get k into 0 bar plus k into 0 bar is equals to k into 0 bar. This is by axiom M1. This is by axiom M1. Because now adding negative of k into 0 on both sides, adding negative of k into 0 bar on both sides, what we will get? We'll get k into 0 bar plus minus k into 0 bar is equals to k into 0 bar plus minus k into 0 bar, which is equals to k into 0 bar plus, okay, here is k into 0 bar plus, this is 0 bar, okay, which is equals to 0 bar. Okay, this is 0 because k into 0 bar minus k into 0 bar is a negative of k into 0 bar. So this is 0, this is again 0 bar. So we will get k into 0 bar, because this 0 bar is a 0 vector. So we will get this is k into 0 bar, which is equals to 0 bar. Hence we have proved which we want to prove. Okay. Now we will prove part 3. In part 3, we have to prove that minus 1 into u bar is equals to u bar. Okay. We have to show that minus 1 into u bar is equals to minus u bar. Means we have to show that minus 1 into u bar is a negative of u bar. Okay. Therefore, we will show that minus 1 into u bar plus u bar is equals to 0 bar. We will show that u bar plus minus 1 into u bar is equals to 0 bar. Therefore, consider LHS. LHS equals to u bar plus minus 1 into u bar. Okay. This u bar can be written as 1 into u bar plus minus 1 into u bar. This is by axiom M4. 1 into u bar is equals to u bar. Okay. Here u bar is common, so take it as common. In bracket remains 1 plus minus 1 into u bar. This is by axiom M2. Okay. Which is equals to 1 minus 1 is 0 into u bar. This is equals to 0. So we will get minus 1 into u bar is equals to u bar. Hence we have proved which we want to prove. Okay. Now we will prove fourth part. In fourth part we have to prove that k into u bar is equals to 0 bar if and only if either k is equals to 0 or u bar is equals to 0. If either k is equals to 0 or u bar is equals to 0 bar, the case turns out to be 1 or 2 and we will get k into u bar is equals to 0 bar in either case. Okay. It is very simple. If you put here k is equals to 0 means we will get 0 into u bar is equals to 0 bar by using case 1. And if we will put here k is equals to u bar is equals to 0 in case 2, we will get k into u bar is equals to 0. Conversely, suppose k into u bar is equals to 0 bar. Okay. Students, see here. Now we have to prove that now either k is equals to 0 or u is equals to 0. Okay. If k is equals to 0, then nothing to prove. Means we will get 0 bar is equals to 0. Okay. Suppose k is not equals to 0. Obviously, if k is not equals to 0, then u bar is equals to 0. Then k being scalar, there is 1 by k such that k into 1 by k is equals to 1. Okay. K being scalar, there is 1 by k such that k into 1 by k is equals to 1. Multiplying both sides scalarly by 1 by k, we get 1 by k into u bar is equals to 1 by k into 0 bar. Okay. Multiply both sides by 1 by k. So we will get 1 by k into k into u bar is equals to 1 by k. This 1 by k is by using 2. This 1 by k is any scalar. 1 by scalar into 0 bar is equals to 0 bar. So this is 0 bar by 2 above. Okay. So this is 1 by k into k. This can be written as 1 by k into k into u bar is equals to 0 bar. This is by axiom M3. Okay. This is 1 into u bar, which is equals to 0 bar. So we will get u bar is equals to 0 bar. Means what? If k is not equals to 0, then we will get u bar is equals to 0. Means what? If k into u bar is equals to 0 bar, then either k is equals to 0 or u bar is equals to 0 bar. This is by M4. Okay. Okay, so we will stop here. In next video we will discuss subspaces. Thank you.